Perfect. Then let's go. Welcome to the Beyond Diagonal RIS webinar series. It's the third webinar that we have today, and this is organized by the Special Interest Group on BD-RIS from the IEEE Communications Society. And today our speaker is Professor Emil Bjornson. He is with the KTH in Stockholm in Sweden. And you can see here the biography. And while you read all the merits, and there are plenty of them, let me tell you how I met Emil first. So I spent 2 years at KTH, 2006 to 2008. And at that time, Emil was a master student in the signal processing department. And from that time on, I'm very happy to collaborate with Emil. Of course, you can see that he has developed very quickly into a very well-known and very visible researcher in the broad area of signal processing, communications, and also machine learning. He has received numerous prizes. Again, you can see the list here. And now we are really looking forward to his talk about Beyond Diagonal RIS. So the procedure is as follows. We have 50 minutes of the talk, followed by questions and answers, where all attendees can raise their hands. You will be unmuted, and then you can ask questions and interact. You can also type your questions in the chat. Enjoy the talk.
Thank you very much for the kind introduction and for inviting me to this webinar series. So I started to first learn about RIS technology already like 6 years ago when I was reading up on to write a paper about what the MIMO related technologies might become into the future. So in this talk, I will start with describing a little bit my view of what RIS in general might be useful for. And then I will describe some of the works on Beyond Diagonal RIS that my research group has done over the last maybe 2 years or so. And that has particularly to do with wideband channels and MIMO channels. And in a way, we have tried to ask ourselves, what are the benefits we can hope to get if we go for the beyond diagonal cases? And this is joint work with a number of people, but particularly my former postdoc at them. So the way that I view RIS is the following, that traditionally you have base stations, sector antennas that had a static radiation pattern, and you schedule users in time and frequency so that they have to take turns to be served. And then you have some users that were standing and got the good gain, and some users that were behind objects and get the bad gain. So that's how the fortunate and unfortunate users here. Then in 5G, we were replacing these base stations with this MIMO-enabled base stations, massive MIMO, for example, which allowed us to have more narrow and therefore stronger beams aiming towards users because multiple use at the same time and frequency. So that was good as long as you had users that had reasonably good propagation conditions. But this unfortunate user here is still going to have this issue that the signal that you can perhaps beamform towards an object will not be reflected towards him unless we are very lucky with how the objects are orientated. And this is when the question comes in, can we deploy something that can control the environment, and there the reconfigurable intelligent surface comes in order to make the users fortunate, all of them, and all having a good wireless service. And in a nutshell, it is like that conventional reflection is determined by the geometry. So if you have a flat surface like this and the signal comes in from a particular angle, then it's going to be reflected with the same angle, but on the other side of the normal. And if you are lucky, then a user standing over here will not be hit by the signal, but it will be reflected as I'm illustrating. And what you in principle could do to resolve this issue would be to take the surface and bend it, and you would then have a surface that looks more like maybe a satellite dish, for example. In this case, the physical shape of the object that reflects the signal will determine where it goes. In this case, we can aim it towards the user. But this is not very flexible if the user moves around, because then you will have to change the bending all the time. And this is where the idea comes in, that can we have a flat surface that can synthesize bent surfaces in different ways? And in order to do that, well, then you need to take the surface, cut them into different pieces, and or remove different kinds of delays or phase shifts over the surface, so that this flat surface synthesizes the reflection of the curved surface. Because basically the pattern that you get when the signal gets reflected is a superposition of many small reflections from these different elements. And if you add some delays, it will behave as if it was. And this is why we are then illustrating surfaces in this particular way, with the coloring illustrating some kind of phase shift pattern that we are adding on top of the flat surface in order to synthesize an object with a different shape. And when I first heard about this kind of concept, it sounded this would be really hard to do in practice. But then I realized quite quickly that it was already doable. So I was invited into a collaboration paper with some people from China. So here's the name of that paper. And they were doing an outdoor experiment with a transmit antenna on a rooftop. And 50 meters away, they put a copper plate over here. And then you have a receiver over here. And the copper plate is just a flat surface here, so it will bounce the signal back towards transmitter, and very little will reach the receiver, because on purpose we used very directive horn antennas in this case. And this was a 6 gigahertz roughly. So what we can see here is the received power over the 2 times 10 megahertz spectrum that we had. So you see some signal power here, and then you have the noise floor outside of it. Then when this copper plate was replaced with a reconfigurable intelligent surface and configured properly, well, one could achieve a much stronger signal gain. And the numbers are not particularly important here, because of course, if you go from nothing to something, you almost have an infinite improvement. So the main point was that I realized at this time in 2021 that this is actually something that is doable, and we can actually implement it. Then whether it is hard to do it or expensive, that's a different story. And we received an award last year for this paper as well, which was kind of giving some more confidence into this technology. So how does a surface like this typically work? Well, in this prototype that we had, you have 20 by 55 column or elements, and each element consists of 2 varactor diodes and some dielectric substrate. I'm not an expert on the hardware design here, but the main thing is that you can tune the voltage over each of these diodes, and the bias between them, so the difference between them, is going to determine how much phase shift you're getting. Here's an illustration of like this. So we designed it for 5.8 gigahertz, and you get different phase responses in the frequency domain depending on what the bias voltage is, from 0, 4, 7, up to 19 volts. We have these different curves here. And since it is this 20 megahertz that are pink illustrated here that we're utilizing, then yeah, we get some different phase shift values in these different cases here. And within this band, and actually, if you would go up even to some 100 megahertz, so a little bit bigger area around here, you have a behavior that is roughly a straight line, even if it's more like an inverted S shape in general. And in such an interval here of 100 megahertz, yeah, you can have this as a piecewise constant line. So basically, an element like this is going to be frequency flat, in the sense that it's basically just creates a time delay. And that is what we want in order to describe. But when we are deploying these surfaces in reality, even if the response of the RIS is frequency flat, the channels are typically not. And that can have a very important impact on the performance that we were getting. So we ran some simulation in a signal processing magazine paper a few years ago. We have a transmitter over here, we have a receiver over here, and we assume that there is a path between them, but it's not line of sight, and we use a typical 3D model for the path loss. And then from transmitter to the RIS over here, we have 200 meters, and we are switching between a line of sight or non-line of sight channel model. And then the receiver sees the RIS, so it's line of sight over here. And if we have line of sight channels to and from the surface, this is the performance we are getting when we are changing the bandwidth. So changing the bandwidth and ramping up the power at the same time, this should lead to a situation where we have a linear increase. And that is what we're getting for all these different curves. But the dotted curve at the bottom is the behavior that you have if this was just going to be a metal plate, fixed one, where its rotation happened to give us a particular reflection. While if we are optimizing the RIS with an algorithm that we described in this paper, we get the dashed line over here. And if we assume that we somehow magically can fine-tune the RIS on every subcarrier, even if you physically can't do that, then you get the red line here. So this is illustrating that there's a big gains to have by having RIS, and we can get these things even if we have a line of frequency selective channel, as long as it is only weakly so. But if we remove the line of sight path here is somehow blocked and we have just a multipath channel around these type of things, well then the performance becomes much worse because you have worth path loss and because we need now to fine-tune the RIS on every subcarrier if we should really get the good performance. And that is not something that we can physically do. And these are some insights that I had when I started to do my work on beyond diagonal RIS that I will be presenting in a moment. So the point is that I think that the big use cases for RIS is typically when you have a line of sight to the RIS and from the RIS to the receiver, but maybe the direct path is very weak. These are the cases where you will get a decent path loss. You can actually benefit from this and also make it work over frequency selective. Before I go into the beyond diagonal RIS, I just wanted to show you this slide here with some recent experiment with RIS that done at my own university. The previous one was in China. So we have a millimeter wave transmitter and receiver. We have a RIS over here. So this is operating at 30 gigahertz. We deploy them at on purpose so that we have a 5-degree instant angle and 15-degree angle over here. And then what we did was to not move anything, but move in the software in which direction we are reflecting the signal. And this is the received signal power that we're getting. So if we try to reflect the signal from -5 to +5, so this would mean that the surface behaves like a metal plate, we get a very weak signal because the signal will just pass in between the transmitter and the receiver. While if we are at the 15-degree angle, which is where we physically had the equipment, we get this peak here, so it obviously works. And after the experiment, we realized that there were a peak over here as well, and that is because there is a laptop behind here that unfortunately were reflecting the signals. This is some of the things that you realize after running experiments that you need to be more careful with where you place the equipment. But yes, I have a RIS in my office, so this is a technology that is mature. And you can find a YouTube video where I'm talking more about this particular experiment. But the question now comes, okay, we have this kind of conventional RIS where each element have a tunable impedance that gives you a tunable phase shift or delay. And then there is a suggestion of the so-called beyond diagonal RIS that this webinar series is about, where you also connect all of different elements between each other. And mathematically, this conventional RIS, you can describe the phase shifts, these set values here, as diagonals along a matrix. And then it becomes natural that this other thing will be called beyond diagonal RIS, where you can also tune how much of the signal that are basically entering one of the elements and is moved inside the hardware to another element before it's being reflected. In this way, you can move around power, for example, between the different ports or elements before you reflect it and have a more flexibility on what you can optimize, more parameters. So from that perspective, a beyond diagonal RIS should always be better than the conventional RIS. The question is, how much better is it and in which situations? So what could be some of the main arguments for this? Well, if you have a really line of sight channel, only one channel, we are up in space, there is even no reflections at all, then it turns out that if you have just a single antenna transmitter and a single antenna receiver, you get a channel to you, which is an array response vector, and you just want to shift the signals in the other direction, and you don't need this cross ports here in between, the impedance in between. The only thing you want is to phase shift and keep the power at the element where they were. So in pure line of sight scenarios, there is nothing really to gain from doing something like that in free space. On the other hand, you have the cases where you have a strong scattering environment, non-line of sight cases, both between transmitter and the RIS and between the RIS and the receiver. And in these cases, this paper that I'm showing at the bottom here were calculated some formulas that are demonstrating that you can increase your signal-to-noise ratio over a side channel in this kind of ID fading with up to 60%, 1.6 times higher SNR. And at the first, when you first see that number, that sounds like a lot. I mean, typical, we talk about 5-10% improvements, and this is 60% improvement. But what we should remember is that the gain that you get when you are reflecting a signal with RAS is squared in the number of elements that you have in the surface. So instead of using a beyond diagonal RIS that give you this gain, you could increase the area of a conventional RIS by just 30%, or shrink it to its reciprocal from that percentage, and this will give you the same gain in this non-line of sight scenario. And since it's also a square, or at least a two-dimensional surface, then if the area have a 30% difference between them, then the length and height have an even smaller, more like 12% difference. So these two risks that I'm illustrating the area of here, they would deliver equivalent SNRs in these non-line of sight scenarios. And you need to look very closely to see that they actually have different sizes. So I'm also not very strongly believing that this is the main use case where you could see the point of that you want to build a much more complicated beyond diagonal RIS compared to the conventional ones. And that's why I set out to try to understand what is the gain in more realistic scenarios where we have MIMO, where we have wideband right sham fading and things like this, to see are there really good gains to obtain in those cases. And this led to two different works that I will present to you, and I will put some of the emphasis on this paper from UCAP this year, where we were looking at beyond diagonal RIS in MIMO communication systems. And this is also related to one of Edward's paper in a way. So here is the setup that we are considering. We have a base station here with NT antennas. We have a receiver here with NR antennas. This doesn't have to be a base station, but a transmitter. And then we have beyond diagonal RIS with M elements over here. And we then have propagation channels, G and F, that are matrices with matching sizes over here. And for simplicity, we assume that there is no line of sight path in between these two different places. Then the end-to-end channel that we are getting will be the G and F matrices, and then we have a matrix that are describing what is the phase shift pattern over our beyond diagonal RIS. And this reflection matrix now have a very general form. And we were assuming the most general form where it is a unitary matrix, just to try to understand what would be the ultimate performance. In many papers, there is also an additional constraint here saying that this reflection matrix also needs to be symmetric, so it's equal to its transpose. And yes, that would simplify the implementation a lot. But in principle, you could implement anything like this with circulators and things like that. So in general, when we have fixed a communication channel here, so we have a fixed realization of our reflection matrix, then we can just view this as a channel matrix H. And then we know how to achieve the MIMO capacity in such a scenario. So we will transmit some kind of signal, X here, which has the dimension of NT, and it should be a Gaussian codebook, and we will have some covariance matrix of the signal we're transmitting that is containing both the precoding matrix and the power allocation from water filling inside of it. And what we then set out to do is to try to do this kind of joint optimization of the precoding and the BD-RIS reflection matrix. So we take this log det formula, which is the classical formula for the channel capacity or achievable rate, and we have the optimization with respect to Q, which is this precoding matrix, and we have that we should pick our BD-RIS reflection matrix as well. And if we just cross out this BD-RIS part of it, well, then the rest of it is a very known problem. So the really interesting thing is, how should we configure our BD-RIS? And here comes one of the result that I was very interested in terms of some kind of structural understanding. Let's take these channels that we have, F and G, from the transmitter to the RIS and from the RIS to the receiver. And we make some kind of singular value decomposition with unitary matrices, U and V. And then we have some diagonal matrices in the middle. And typically this will not be square matrices, but rectangular matrices. So then U and V are still square matrices, unitary matrices of different sizes, while D will be a rectangular matrix where you only have some of the diagonal entries will be non-zero. But those that are non-zero are placed in decreasing order, and that is an important thing from a notational perspective here. So what we were showing is that what you want to do to have the optimal BD-RIS response matrix is to take a matrix which takes the singular vectors from one of the matrices and the singular vectors from the other channel matrix and multiply them together like this. And this might look like it is some kind of arbitrary matching together of them, but since we were ordering the signal values in decreasing order, what we actually are doing here is that we are pairing up propagation paths from the SVDs in the order of strength. We pair up the strongest path from transmitter to the RIS and the strongest path from the RIS to the receiver. So here is an illustration of that kind of concept. To say that there are basically 3 paths from the transmitter to the RIS and from the RIS to the receiver, then the strongest path will probably be a line of sight path, the red one here. So we take the corresponding beam direction coming from our SVD, and we transmit one stream in that direction, and then we configure the RIS so that it reflects the signal in the direction that will give us the strongest signal to the receiver. And then we look at the second strongest, which happens to be the path through this object over here, and then we pair up it with the second strongest path to the receiver. And then the green one is the third strongest. And you can keep on doing this, pairing them up in order of strength. This is the optimal thing, and so far, there isn't even any notion of SNR in this. So whatever transmit power you're having, you should pair them up in this order of strength. Then comes the optimal precoding matrix. That one should, it usually happens, be based on the singular vectors of the channel that we're getting, which is the G matrix here. You will get the singular vector from that one. And then you will have a diagonal matrix in the middle, which is the water filling that tells you how should we put the power over the different, this free path, for example, that I was illustrating. So you basically get a capacity value, which is a summation over the number of data streams that you are transmitting. And in this case, that will be up to the minimum of the number of transmit antennas, the number of receive antennas, and the number of RIS elements that we're having, because this is giving you the largest rank that our H matrix, this F, the response matrix, and G will give you. And we have a summation of log 201 plus the SNR that you're getting for each of these different POFs. For each one of them, you have the ith strongest singular value squared from the F, the ith stronger from G, and then we have the power that we allocate from this one, need to come from water filling. So we have a very nice description here geometrically about how the optimal BD-RIS configuration should work in the MIMO case. Some interesting things that happens if we have very high SNR, then we know from the water filling allocation that we should eventually divide our power equally between our k different dimensions that we can have in our channel matrix. In this case, it actually doesn't matter anymore. We are pairing up the path from transmitter to the RIS and from the RIS to the receiver. We could take this singular vector matrices, and we can add some kind of permutation matrix in between and pan them up in whatever order we like. Eventually, at high SNR, all of those options will become equally good. So it's particularly important to do the pairing that I suggested when you have lower SNRs, which you probably have in practice. And other thing that we were also looking at, what if we would have kind of the best kind of channels you would have in a MIMO scenario, namely that the channel G and F, all of them have singular values that are equally large. This is the best thing you can have from a MIMO communication perspective. So in this case, you have K such singular values, and the summation over log 201 plus the expression, all of the terms here at the inside becomes the same, and therefore there is no reason to do a power allocation that is anything else than equal power allocation. So this is the expression that you're getting, K times log 201 plus, and then you have an SNR term here. And in these cases, it also, there is no notions anymore about the strongest, pairing up the strongest with the strongest, the second strongest with the second strongest, and so on. The only important thing that is left is that we should get K equally large singular values, and if you have fewer BD-RIS elements, then you have transmit and receive antennas. Well, in these cases, any BD-RIS configuration will achieve this goal because, all dimension leads to one of your receive antennas. So the challenge is really that when you have many more elements in your BD-RIS than you have at the transmitter and receiver, then there is only some directions that you can reflect in that leads towards the receiver, and there's only some directions from the RIS, from transmitter, where the signal, there will be signals coming from. So those are the more challenging scenarios. The more RIS element you have, the harder it is to select the best BD-RIS configuration. So that leads me to some numerical results we'll want to present. What we are considering over here is a Rice fading channel with a 3 dB K factor. So it is relatively much scattering in such scenario. In many Rice fading channels, we have some 8 to 10 dB as our K factor. Then at transmitter and receiver, we have uniform linear arrays with lambda/2 spacings. In the BD-RIS, we have uniform planar arrays, and usually the elements in RIS are relatively small, so we assume the lambda/4 spacing here. And we are randomizing the different angles, both in azimuth and elevation. We have 20 different clusters per channel, with some equal strength of them and random directions. So this is inspired a bit by how you would do things in 3DPP, even if they usually are clustering them more in particular directions. We have 16 antennas at transmitter and receiver, and we are defining our SNR for what we will get element in the RS if we have equal lambdas here. And we did Monte Carlo simulation to get the results I will be showing. Here is the first result. And we are showing the capacity in bits per second per hertz versus the number of RAS elements. We start with a number that is smaller than the number of RIS elements, number of transmitter receive antennas. We had 16 transmitter receive antennas. We start at 9, then we have 16, 25, 36, 49, and 64. And there are 3 different curves here. The red one is what we are getting with our optimal structure. The blue one is what we are getting with a paper that comes from Edwards Research Group. To be fair, I should point out that this paper is having an extra constraint that is saying that we should have a reflection matrix that is also symmetric. So it should be equal to its transpose. So the gap between these curves could be caused just because we have relaxed that constraint. we have a closed form non-reciprocal design, while Edward had a reciprocal design obtained with some manifold optimization methods. But the interesting thing here is really the comparison with a conventional RIS, which is the black curve over here. So we can see that the more element we have, the more the gap is increasing, and we particularly outperform RIS in those cases. So I will now move on and show you some further numerical results. So one thing we were looking at was the sync to noise ratio and sweeping it from a very low number to relatively high numbers. And remember, I had this result saying that ISNR, it doesn't matter how you pair up your different singular directions from the transmitter to the receiver. It doesn't have to be strongest, second strongest, third strongest, and so on. Any random order would work equally well. The black curve is which at a random order. The red curve is what we are having, and the blue curve is once again from paper. And what we can see, the interesting thing is the red and the black curve. So at low SNR, it really matters very much that we are pairing up the strongest path, because we only do allocation to the strongest path, and then we turn on the two strongest ones, then we need to pair them up together, and then we keep pairing them up in that order and get the best performance. But as we are approaching high SNR, it doesn't matter how we are pairing them up anymore. We are approaching the same limit up here. So yes, it's more important how you configure your BD-RIS at lower sync to noise ratio. Then we will have another look at what happens when you have a number of elements that are vary. And in this case, we assume that all of the singular values in our matrix to and from the RIS are equal. So they are basically semi-unitary channel matrices. And then at 9 and 16 elements, remember we have 16 transmit and receive antennas, then the BD-RIS and the conventional RIS are equally good. And this has to do with the point that any response matrix is optimal, at which we were proving mathematically. So in those cases, one of the many ones is a diagonal one. You can use that equally well as anything else. But as soon as we start to have a difference between the number of transmit receive antennas and the number of RIS elements, we see that the curves are separating and we have a better performance that is, and a gap that is growing the more happy. So now I will go over to the wideband case. And now we would take a step back, and it will be a size scenario with wideband. So we are separating those effects. We don't have any result with both MIME and wideband yet, but it's something that. So what is the thing happening in a wideband scenario? Well, in this case, we have a transmit antenna over here, we have a receive antenna over here, and we have our BD-RIS over here. And there are multiple paths. I call the paths from transmitter to the RIS, they're LT, number of them, and they can be ordered in whatever way you like. And we have LR paths from the receiver. And the particular subcarrier, new here, the channel coefficient from the transmitter to the receiver consists of a number of different parts. One thing is a coefficient that just describes some kind of static path that doesn't go through the RIS through some objects over here. So if it exists, it will be added over here. Then we can take any of the paths that comes to the RIS, so that's a J index, and any other path that goes from the RIS, that's a K index, and they are coming from some particular angles. So these are the incident angles, and these are the outgoing angles. No, it's the other way around here. So I is the incident angles. So from what direction does the signal come here? And what is the outgoing angle? It is this here. And you get those A here, which are array response vectors that are defined by the geometry here, which in this case was a uniform plane array. And you take these ones and you multiply them with the BD-RIS configuration matrix. And notice now we have changed from theta to psi, but apart from that, it's exactly the same thing. So this is how one of the paths is going to be. Maybe the blue one here together with the purple one. depending on their angles. And then there will be a coefficient that is complex and tells you how strong is that combination of paths and what is the phase shift that it's creating for the first element that doesn't have any phase shift in this expression. And then we sum it up for all the different paths and through the static path as well. And this is the channel you will have a particular subcarrier. And we consider S subcarriers. And we can notice that the subcarrier index is only determining these coefficients here. The angles, the geometry is the same regardless of the subcarriers. So this is where it enters. And when you model these coefficients, what you need to remember is that a particular combination of paths will create some kind of multi-tap channels where you have some coefficient that tells you for these different channel taps how strong is a signal and what is the phase shift that it's providing you with. We have up to T+1 channel taps, and these coefficients are basically the DFTs, so discrete Fourier transforms of this time domain representation of the static path and of the different paths through the different element. And yeah, the whole thing might look quite big in terms of notation, but very quickly one can bring it all together. The important thing is that there is an underlying channel model that determines the angles and these C parameters. And as far from that, we can get a much simpler expression. So the first thing you can do is to take the expression that I had in the previous slide and give it some simpler names. Let's call it H nu for the static path. And then instead of writing everything in the order that we did, we can rearrange the order using some trace constraints and get the BD-RIS configuration matrix here in front. And then you have a big matrix here that is consisting only of the array responses and the strength and the sum of the paths. And this matrix, we call it H nu. And now we have this lower and uppercase H matrices and scalars that representing our channel in different areas. And what you want to do is to calculate what rate you can get or capacity and try to get as good performance as possible. So once again, for a fixed realization of our reflection matrix for the BD-RIS, we can calculate the capacity that you are getting. It's a summation over our subcarriers. We have log 201 plus SNR. So it's this term here in absolute value square, exactly using this new simpler notation. And we have some power allocation and some noise variance, and the power allocation can be achieved with water filling over our subcarriers in this case. And there is some scaling factor in front here with the bandwidth divided by T plus S, which this is the number of subcarriers and the cyclic prefix that we need to spend in order for this to work in a system. And once you know what your capacity here is for a particular fixed reflection matrix, well, you can optimize this matrix. And it starts to be kind of complicated to optimize it directly here. So what we propose to do is to have some simpler metric to optimize. Namely, we would like to maximize the total received power over all of my subcarriers. So we take this term over here, we sum it up in absolute value square over all our subcarriers, and then you can rewrite this in a number of different steps and come to a point where you can write your expression like this, kind of quadratic form, where this is a vectorization version of our BD-RIS reflection matrix. And in general, it still needs to be uniform, unitary matrix. First, we relax it, so we only keep that where normally it needs to be equal to the number of elements. And then we have an iterative solution in our paper where we are optimizing this matrix step by step and update the power allocation step by step until we converge into something good. And we have a number of closed form solutions along the way. But in the interest of time, I will not bore you with those exact formulas. But instead, show you some results. So the nice thing with this wideband channel model that we're describing with you is that we can easily vary the bandwidth and get a spatially consistent environment where the number of taps get cut into more taps we have more bandwidth. Here is the capacity that we are achieving, depending on how much bandwidth we have when we start with 6 megahertz and we go up to 30 megahertz. And first, we have non-line of sight channels only everywhere. And I think we even dropped that off in this simulation. And the bottom curve is what we get with a random BD-RIS configuration. The top curve is what our algorithm is delivering. And the curves here in the middle are we get with something called strongest tap maximization. This was what people were often suggesting for scenarios like this with conventional RIS, that you look in the time domain for the channel tap with the strongest signals, and then you try to maximize that one, which doesn't perform particularly well in a non-line of sight scenario, but it might work in the line of sights. And then we have a way of configuring a conventional RIS, and that's the blue curve. What we can see now is that the more bandwidth we have, the more variability the channel will get over different subcarriers. And then the BD-RIS is showing its ability to configure itself to have a better trade-off between the different carriers. So you can see that it has the smallest slope out of all of our methods over here. So it is really able to handle this multipath environment. Let's now fix the case here with 30 megahertz, and instead vary the Reischen K-factor. So here we had non-line of sight, which is basically the same thing as having like a minus 20 dB K-factor in the Reischen failing case. And now we start increasing the K-factor instead. So that's why you see all the curves are starting at the same points as they ended. And what we can now see is that apart from the random case, many of the curves are starting to go upwards. Particularly our proposed method goes up, and the blue curve here, which was with the conventional RIS, is going up. And that is demonstrating the point that it is very good of a line of sight path when you're working with RIS in general. Particularly in SIG cases, you get a more stable channel. The channel is not varying very quickly over the different subcarriers. But we also have the point that the conventional RIS is catching up with the BD-RIS case here, which was something I was talking about earlier as well. So at practical K-factors, if you read the specification for 3DPP, they usually suggest simulate with some 8 dB or something like that. Well, then you will be somewhere over here, which is where the BD-RIS is not showing as much improvements anymore. So to start to sum things up, BD-RIS is a more complex thing to build, and to my understanding, there is no experimental equipment yet that is demonstrating this, while could even buy a conventional RIS from a Taiwanese company. But so therefore, I think it's really important to identify when the extra complexity is really worth it. And what we were seeing was that the BD-RIS is better at handling complex propagation environments, which you will come across with MIMOS channels when you have a surplus of elements in the RIS compared to number of transmit and receive antennas, and you have a rich channel. And it also happens in wideband channels when you have non-line of sight cases, so you have large variations over the subcarriers. Well, then the BD-RIS can find a much better combination of them. However, the conventional RIS gives you the same capacity as BD-RIS if you have small sizes, small number of elements, or you have line of sight dominant channels, which is kind of problematic because I think the most important use cases for RIS in general, at least that was what I used to believe, are cases where you want to create this kind of virtual line of sight scenario. The signal goes from transmitter to the RIS over line of sight and from the RIS to the receiver over line of sight, but you have a blockage in between them. And in those cases, BD-RIS really excel. But I don't want to end with a very negative view of things, but I think now maybe a more promising scenario is to use BD-RIS for multi-use environment. We just the other day uploaded a new paper about this. This is a scenario where we have a base station, multiple antennas, and we have single antenna users. And then one of the assumptions we are making here is that we have an IID fading, so a high rank channel between the base station and the BD-RIS. And this is something that one can potentially wonder in which scenarios would you actually have that and still have a good enough SNR. But apart from that, the nice thing is that regardless of if you have line of sight or non-line of sight channels to the individual users, the channel matrix that they are creating together with each other will have good rank properties. And this was also one of the main selling points for why multi-user MIMO is more promising than point-to-point MIMO in the massive MIMO literature. So this might be a more promising scenario where a BD-RIS can provide much bigger gains. And here's an illustration of this, and the curves are a little bit dense, but we are considering 5 transmit antennas and 5 users, and we have a number of reflecting elements that are increasing from 8 upwards to 64. And I have mostly talked about fully connected BD-RIS or only so far, so all the elements can share with each other. You can create any unitary matrix. While at the bottom here, we have single connector, which is the conventional RIS. And we can see that in this scenario, there is actually a very substantial gain here. And even if you have some kind of group connected BD-RIS, some kind of simplified versions of it, we can still provide some gains. So right now, my focus for finding good use cases for BD-RIS is more narrowing into the multi-user MIMO case. And with that, I would like to thank you for attending, and I will be happy to discuss the topic more with you in the Q&A session.
Thank you very much, Emil, for this interesting talk and presenting the 2 published papers and also the ideas of the very recently published work. Now we have time for questions. You can either raise your hand or you can type your question into the chat. So while everybody is typing and wondering about questions, I would like to ask a question with respect to the first part of your talk, where you had a closed form solution for the optimal unitary RIS matrix. Can that result be generalized to the case when you have a direct channel component? Because on your slide, you have shown that there might be a non-line of sight direct component of the channel that would be available too, but it's not so strong. So maybe not a direct line of sight, but non-line of sight conditions.
That's an excellent question. And to be fair against your paper, your paper can handle that scenario and we couldn't. No, I haven't found a way of merging these things together. So this is something that we are working on when we're trying to extend the work, but it is not immediately obvious to me how to do that.
Can you explain what the main difficulty is there?
Right. So let's see if I remember here. So you will basically have an additional term that you will be adding here where I'm pointing the mouse, right? And what we try to do is to match together singular values in F and G with each other and pair up the strongest and the second strongest and so on. And in order to, but then what matters in your capacity expression is what singular values you get for H. And if you have an additional term that is added here, then how they add together, that's not very clear. And we are not touching the singular vectors on the outside of F and G, only the ones at inside, and match them up together. So yeah, I don't see how that can be done, except if you are making particular assumptions on that this matrix here have the same maybe SVD. Yeah, the SVD of it has the same outer singular vectors as F and G has.
Yeah. Thank you for the explanation. I understand. So we have one question in the chat asking for my final year project. Is it worth to progress and do further research on beyond diagonal RIS?
Great question. So I think that the research that we are doing, particularly in thesis work, doesn't have to be motivated by that we think that they will be very groundbreaking and affect the industry or real world deployments in any big way. But I think what you want to demonstrate in such a project is your ability to formulate a research problem that have some relevance and solve it with some established or new methodology. And there, I think you can definitely work with BD-RIS, and I have some additional works that I didn't present today where we were throwing in BD-RIS as well into the papers, partially because they are mathematically nicer to handle than conventional risks in many of the optimization problems. So I think that if you're considering to do some kind of risk optimization problem in your thesis, then yeah, potentially throwing in the BD-RIS into the picture will be a useful thing to do to make some of the math nicer.
Mm-hmm. Yeah, thank you. We have another question regarding the number of RIS elements. Most of the presented cases were with a small number. Can you comment on this? Because many common large RIS have hundreds or even thousands of elements.
Yes, exactly. So the RIS I have myself is for millimeter waves, but it has 1024 elements. And yes, this is something that I could talk a long time about potentially. So the one issue that I have with a lot of the research on RIS is that, and we just talked about that I did it myself. I was throwing out this that we normally would have added here.
Mm-hmm.
That means that as soon as you go from 0 to 1 RS element, you would get a infinite improvement in performance. And they go from 0 to something. And therefore, you can show good performance already with a reasonably small risk, as long as you tune your transmit power, so bandwidth and things like this, so you get a decent SNR. In practice, one should have that extra path here as well, and it might be very weak, but in many frequency bands, it's not 0, and therefore you would need a decent number of antennas. And to some extent, this is also what we were playing with in the paper that I was showing some result over here, that when we switch from line of sight to non-line of sight, one of the paths, then the path through the RAS became weaker, relatively speaking, and therefore the direct path here made the gain, the relative gain, smaller. So yeah, I've totally agreed that in practice you will probably have hundreds of elements, but it depends on the frequency band, and it's not always that the simulation that we're having are considering the most realistic parameter values.
Mm-hmm. Yeah, thank you very much. And of course, we will have now also received a question about the perfect CSI assumption on the two channels from and to the RIS. So have you studied how imperfect CSI affects the performance?
I didn't do it specifically for BD-RIS, and the reason is that I wanted to find some really good use case for a technology where we could have a big gain compared to RIS. And then I didn't really care if estimation problems or anything like this. If there is a good enough gain for a technology, then we can probably figure out the channel estimation problem. But I understand that the channel estimation problem is harder to solve with the BD-RIS because the cascaded channel more coefficient that you really need to know compared to the diagonal RIS where you have fewer parameters that you need to know.
Hmm. And another important question is about or methods to control the interference that is created for other frequency bands. So we have one question where you have a specific operator that deploys a BD-RIS, and what is the best way to mitigate interference among operators in the same areas?
Right, and I would guess that this refers to something that we have been calling interoperator elimination, and I'm currently in Copenhagen where I talked about this yesterday on the spectrum management workshop. And I think that if we start deploying RIS in outdoor networks, we would have to have some kind of coordination on where you deploy them, so that how frequently or when you are updating the configurations, because there will be when you're switching it to achieve some good performance in your band, you're also changing the performance in the other band. And that is not necessarily a bad thing. It's only a bad thing if the guy operating the other band estimates the channel, thinks that it is going to get a particular performance, and then you degrade this performance.
Right.
So we need to have some kind of coordination rules there. And if you can't have that, you need to know where this other risk is, so that you, with your multi-antenna base station, can try to filter out that.
Yeah, I see. So you should not destroy the TDD structure that allows you to exploit the channel knowledge and to predict very well the channels in up or downlink from the measurement from the other
Yeah,
direction.
exactly. And in today's 5G networks, when you do TDD, you are forced to synchronize between operators. So they do uplink and downlink at the same time to control their other band emissions. And when you do that, it becomes natural that you send reference signals at the same time and estimate your channels at the same time. And then if both operators changes the RAS after the channel estimation, none of them are going to get the channel that they thought. And that is sort of the essence of the problem. But I think one can solve it, but it needs to be dealt with both in algorithms and in some kind of rules, I think.
Yeah, okay. And another question is related to simulation software. So, are you using some specific software for that, or can you recommend a software for simulating RAS?
So what I have been using in the simulation I was showing is just to implement mathematical formulas in MATLAB. So it's simplistic from that perspective. But I think particularly when you go into more intricate hardware designs like BD-RIS, that one also needs to be mindful, how good are those models? Do we need to have a better model that is capturing intercoupling and losses that you will have at the inside of the BD-RIS? And exactly what, if there are some specific hardware for that, I don't know.
Okay, so another question is related to the benefits of BD-RIS compared to diagonal RIS. So let's assume you not only want to maximize the received power at one position, angle, or location, but at the same time you would like to decrease some received signal power at other locations, for example, for secure communication. So do you think their gains would be larger in these scenarios?
I think so, because in a way, it is rather similar to this multi-user MIMO scenario that I showed here in the end. It's just that instead of maximizing the power of multiple paces, you want the paths not to add up constructively, but destructively. So it's a little bit different metric there. But yeah, I think you definitely have more parameters to tune, and you don't want a diagonal risk
Mhm.
structure anymore.
Yeah. I think so too. If you have more degrees of freedom in your optimization for the BD-RIS, that should usually lead to improved performance if you have
Yeah.
more constraints, yeah, or more objectives. I would say the last question, because we are running out of time a little bit, is about the switching from a diagonal RIS to a beyond diagonal RIS configuration. Is it possible to switch in real time between these configurations?
I would say that I would view this as two different pieces of hardware, that you either deploy one or the other. And if you have chosen to deploy BD-RIS, you can operate it the diagonal RIS if that happened to be the optimal thing to do, which it might be in line of sight scenarios. And yeah, you don't need to switch in that particular way. Then when we are on topic, we can say the switching time really depends on hardware implementation as well. I think one can switch diodes in millisecond time, but not necessarily so easy to build a big RIS with many elements that need to switch their diodes at the same time, do it in parallel rather than sequentially. So exactly how quickly you can do things I think it needs to be demonstrated in prototyping.
Yeah. Yes. So I would say that we have almost answered all the questions. Thank you very much, Emil, for this nice presentation, and thanks to the audience for the nice discussion after the presentation. I wish you all a very nice remaining Wednesday and hope to see you soon.